Okay, last section in chapter 5. Putting it together. Which method do I use? Okay, so first of all, here's a nice little flow chart. First of all, you decide, ask yourself, are you finding the probability of a single event? If yes, you ask yourself if the outcomes are equally likely. If yes, then here's your formula. If no, is it possible to get empirical data? Yes, here's your formula. No, subjective probability. Right? Okay. If it's not a single event, then it's either going to be an or, and, at least. And we've got formulas for each of those. All right, let's look at some examples. In the game show Deal or No Deal, a contestant is presented with 26 suitcases that contain amounts ranging from a penny to $1 million. The contestant must pick an initial case that is set aside as the game progresses. The amounts are randomly distributed among the suitcases prior to the game. What's the probability that the contestant picks a case worth at least $100,000? Okay, is this a single event? Let's think about the flow chart. Okay, yeah, he's just going to pick a suitcase. Okay, are the outcomes equally likely? No. Is it possible to get empirical data? Yes, this is our empirical data. It gives us that list. Okay, well then we have a formula for it. Okay, the probability that he gets at least $100,000, so more than or equal to $100,000, is there's 7 cases that have 100,000 or more in it out of 26, right? Out of 26 possible choices. Okay? Okay. According to a Harris poll in January 2008, 14% of adult Americans have one or more tattoos. 50% have pierced ears, and 65% of those with one or more tattoos also have pierced ears. What's the probability that a randomly selected adult American has one or more tattoos and pierced ears? Is this a single event? No, it's an and, right? Okay, so with the and, my question is, are the events independent, right? No, I can't determine exactly that they are. Okay, so we have a formula for that. The formula that they have tattoos and ears pierced, right, would then simply be the probability that they have tattoos times the probability that they have their ears pierced given that they have tattoos, right? They're not independent. Okay, so the probability that they have tattoos, 14%. Okay, and 65% of those with one or more tattoos also have pierced ears, right? And we can just put that in our calculator. .091. Okay, so the probability of selecting an adult American at random who has one or more tattoos and pierced ears is a little over 9%, right? 0.09. Okay, to determine the appropriate counting technique to use, we need the ability to distinguish between a sequence of choices and an arrangement of items. So we also need to determine whether order matters. So keep in mind that one problem may require several counting rules. So here's a little flow chart for your counting rules. Are you making a sequence of choices? Okay, yes. Then are the number of choices at each stage independent? Yes, we've got our counting principle, right? No, use the tree diagram. Okay, are you making a sequence of choices? No. Then does the order matter? If not, here's your formula. If yes, right? Are you selecting all in objects or only R objects, right? So depending on if you're going to just do the factorial or the permutation. All right. So the Hazelwood City Council consists of 5 women, 5 men, and 4 women. How many different subcommittees can be formed that consist of 3 men and 2 women? Okay, let me get my pen and let's think about our choices here. Okay, are we making a sequence of events? Okay, no. Does the order matter? No, it's just a committee, right? There's no ranking to it. So let's select the men and the women. Okay, to select 3 men, we have 5 men, and since the order does not matter, that's a combination. And then to do the women, there's 4 women, and we're going to choose 2 of them. And remember your fundamental counting principle, you multiply, and we can just put that in our calculator. So 5 choose 3 times 4 choose 2 and we get 60. Okay, there are 60 possible subcommittees that contain 3 men and 2 women. All right, let's look at one more. On February 17, 2008, the Daytona International Speedway hosted the 50th running of the Daytona 500. Touted by many to be the most anticipated event in racing history, the race carried a record purse of almost $18.7 million. With 43 drivers in the race, and how many different ways could the top 4 finishers occur? First, second, third, and fourth. All right, it's an ordering problem. We're ranking them. So really, I've got a couple of ways that we could do this. We've got 4 places, right? So there's 43 people that could come in first place. But once that car comes over the finish line, then there's only 42 cars left, and then 41, and then 40. Or this is the same thing as 43 permutations taken 4 at a time. Either way. Okay. 2,961,840 different ways that the top 4 finishers could occur. Okay, so that finishes up chapter 5. Let me know if you need anything.